Good morning, everyone. So we're going to start from just a couple slides back from the place that we ended. Last time, we left off talking about this half-wave diode rectifier as shown here with a filter capacitor as well as a load. And so why were we discussing this? Right, we know what a half-wave rectifier does. Half-wave rectifier takes something that looks like this and essentially turns it into something that looks like this. But still not very useful for doing something like charging a laptop battery or a cell phone battery. Therefore, we use the capacitor, the filter, in order to try to get something that looks more like a static DC. And so we saw that this was a transient analysis with a loaded resistor, and we used Laplace in order to solve for the transient response. And what we saw was that the output voltage looked like this here. Sorry, I'm not doing a very good job of tracing it. And the current through the load looked like this right here. And we also had our diode current. Anyway, to make a long story short, we have a charging interval, a conduction interval, as well as a discharging interval. The discharging interval is much longer than the charging or the conduction interval. And I won't go too much into this, but this was the result of our Laplace analysis. Now, the one thing that we did point out at the very end of last week's lecture is that when the ripple is small, we can think of this as being relatively linear. And the example shown here, I would count it as relatively small. But if we have a larger discharging interval, a larger ripple, then the exponential shape will be more evident. And so we use Laplace in order to solve, but right after this, and now I'll go forward to a couple of these slides, we saw there were some equations, right, that we could use to estimate the ripple height, to estimate the conduction interval. And again, I'm sorry about all these extra numbers, but you can refer to these equations in the textbook or in the PDF version of the notes that I've posted online, and it shows everything more clearly. I think I've gotten this solved for the next lecture, so we shouldn't have this issue anymore. And right, so conduction interval, amplitude of the ripple, so on and so on. That brought us to the next topic, and that's where we stopped, limiting and clamping circuits. So what's a limiter circuit? A limiter circuit is one that limits the voltage output. So if we have an input that looks like this, and we wish to limit the output at these values, a limiter circuit would generate something that looks like that, physically limiting the voltage. And so you can see here that on the x-axis we have VI, on the y-axis we have VO. Now, K is going to be the gain between the output and the input. If we assume this is 1, then the input-output relationship would be 1. And over here, what we have is the high and the low end of the limit, L plus and L minus. Now, if K is equal to 1, then this point right here will be L plus, L plus. If we have the K, then that'll incorporate the K value over here. Anyway, as you can see, right, it limits the output beyond a certain value. This looks very similar to the saturation of an op-amp, actually. And so you could see that the op-amp, it's not really meant to be used in that fashion, but indirectly or in an unintentional way could be used as a limiter. Okay, so a passive limiter circuit is what we're talking about. It has a linear range and a nonlinear range. This is going to be linear right here. And then over here we have a non-linear range. K is generally going to be, well, not generally going to be, K is going to be less than 1. it's a passive circuit, so we're not going to be able to generate an output that's greater than our input. And so examples include a single limiter to operate in a unipolar manner, or a double limiter to operate in a bipolar manner. And don't worry, we're going to show some examples of that in a second. So VO is equal to K times VI in the linear range, and then a constant value outside of the linear range, what we call the nonlinear range. Again, this right here, and I'm running out of space, but this right here is our linear range. Over here, our nonlinear range. This expression down here simply restates what is above. So in the linear range, which is VI in between the two boundaries, V out is equal to K times VI. And then outside of the linear range, it's set to a constant value. Now, soft versus hard limiters. And you can see here in this picture, there's a little bit of some animation. The hard limiter is shown in red. The soft limiter is shown in blue. Hard limiter has that sharp boundary between the linear and the nonlinear regions, and the soft limiter has more of a curvature to it. So, and depending on what application you're looking at, one or the other may be advantageous, and obviously there's different implementations. Some yield soft, some yield hard. Again, we're going to go into specific examples in a second. So how are limiter circuits applied? There's various applications. One is in signal processing to prevent breakdown of transistors within various devices. I'm sure you can imagine that it serves primarily a protective purpose, where it allows us to prevent another device from having a voltage applied across the terminals that's beyond what it can handle. Okay, so now this slide looks very busy. I'm going to spend a second going through each one. Now, this is not something that I expect you to memorize. I've talked a lot about memorization in this class previously, and how, especially for things like this, it's about the understanding of how to interpret the figure, how to interpret the circuit, more than memorizing, okay, I remember how, what the VI characteristic or V in output characteristic for this specific type of limiter is. All right, so let's go through them one by one, and you can see, you can draw sort of a boundary there to separate the different types. So we have single limiters that employ one diode. That's here and here. Depending on the direction of the diode, that will determine whether the limit is placed on the upper or the lower bound. You can see this is a soft limiter. There is some curvature in there. And the K value equals 1. Diode points downward. It's a limit on the high end. Diode points upward. It's a limit on the low end. And that makes sense, because if you think about this, for negative voltages, the diode will be blocking. And so it really won't be participating in the circuit at all. For positive voltages, when this diode is conducting, right, we know that the voltage across that diode when it's conducting will be approximately 0.7 volts, and so it'll provide a limit. The opposite occurs for this one shown to the right here. When the voltage is negative, this diode will be conducting, which then will set that limit. Okay, so next we have double limiters that employ two diodes of opposite polarities, and as you can see in the figure, what that does is it provides us an upper and a lower limit. So, so this one corresponds to this. Pretty much the same behavior as these two. Number 1 and number 2. This is number 3 is simply a combination of those together, where the diodes fire depending 1 or 2 fires depending on whether the voltage polarity is positive or negative. Sorry, one second. I'm just going to put this in airplane mode so I don't get any more notifications. Right, so depending on which diode is forward biased, right, you would hit the corresponding limit. Okay, now, the linear range may be controlled via a string of diodes and DC sources. So this yellow box is talking about this example over here. And so if we want to raise the limit from 0.7 volts up to, let's say, 5.7 volts, then what we can do is place a DC source in series with the diode. So therefore, when this voltage VI is positive, the diode will conduct. We'll end up with a 5 volt difference here and 0.7 volt difference here. And so the result is a limit at 5.7 volts. Now, you could also do this using a string of diodes, which I don't think is really shown on this slide. I'll try to divvy out a little spot here. So let's say we have a resistor and we have 3 diodes in parallel like that. So what would be the limit that this provides? It would provide, so that the diodes are pointing downward, so it's going to provide an upper limit, and when they're conducting, each one of these will yield an 0.7 volt difference across them. So, and sorry for drawing it so small, so this would provide an upper limit of 2.1 volts. So that's the reason why it says the linear range may be controlled using a string of diodes, which would be this here, or DC sources, which is the example shown. And last, Zener diodes may be used to implement soft, or perhaps I should say softer limiting. Again, it's a little bit relative. So I called this a soft limiter up here, but I guess the edge is pretty sharp. So we'll call this a hard limiter, and then when you use a Zener diode, it greatly it shaves off the edge of the limit, or it shaves off the edge between the linear and the non-linear regions. And I know that we haven't talked a lot about Zener diodes in this class. I've relegated that largely to the textbook. If we have some time at the end, perhaps we'll come back. So I know this slide looks very messy right now, but it is a good overview of limiters. Now, what sort of questions would I be asking you about limiters? I mean, this is one where it's really just about understanding what does what. You would have access to this. I wouldn't expect you to memorize it, so I would give you access to the different configurations with the V in out characteristics, and it would just be a matter of understanding what's what. Sorry about that. Okay, so here at the end of chapter 4, what we're doing is going through some additional diode-based circuits, in addition to the ones we've talked a lot about, which are the regulator and the rectifier, the logic gates. And we're going through them in a faster manner. We're not placing as much emphasis on them. So limiter was one of them. And then here we have something called a DC restorer. So what is a DC restorer? It's a circuit which removes the DC component of an AC wave. So if you look at this wave right here, okay, what we have is an AC wave. It's a square wave, and it has a DC component offset of negative 6 volts. Okay, down here. So the DC restorer is a circuit which removes the DC component of an AC wave, which is essentially going to push it upward such that the minimum does not dip below the x-axis. And the circuit is relatively straightforward. The design is not very complex. You have your input signal, you have your cap, and you have your diode. And so the result is you go from your input that looks like this, and you get your output that looks like this. If I were to do the same thing with a sine wave, so let's say we had something that looked like this. It varied between 5 volts and negative 5 volts. The output yielded, so if this is 5 and this is 10, the output would look like like that, where again, we would not dip below the x-axis. Another circuit that we're going to look at is called the voltage doubler. So this is a very useful circuit. It allows us to increase the voltage by a factor of 2 without having to use an amplifier. So it's a passive circuit. There's not much to say here. As the name suggests, it doubles the voltage. So if we have an input, which is a sine wave here, and we run it through this circuit, which is composed of 2 different capacitors and 2 different diodes. I'm not going to go through and do a detailed derivation or analysis of how this works, just because it's not really a huge focus of this course. Application would be more what we would worry about. But this is the design. You can utilize it, and it doubles the voltage. So if we had, I don't think there's any really need to draw it. If you had an input that looked like this, it would multiply by 2. Okay, this is homework number 10. When I do the live lecture, I am going to talk a little bit more about the homework and how we're going to handle that, but this is your next homework assignment for right now. Like I've talked about before, there are some special homework problems that I have saved from previous years, so I encourage you to take a look at it, and perhaps this is something we can examine during one of the recitation sessions. Okay, so that's it for chapter number 4. I'm going to read through the summary briefly, and then perhaps today we haven't really used up that much of our time. So we'll start on chapter number 5, give an introduction, and then see how far we get. So summarizing how the diode works, in the forward direction, the ideal diode conducts any current forced by an external circuit while displaying a 0 voltage drop. Now this, again, is assuming we're using the ideal model. The ideal diode does not conduct in the reverse direction. Any applied voltage appears as a bias, reverse bias across the diode. The unidirectional current flow property makes the diode useful in the design of rectifier circuits. Right, take something that looks like this and can make something that looks like this. The forward conduction of a practical silicon junction diode is accurately characterized by the relationship I equals e to the v over vt. This is the same expression that we derived from our work in chapter number 3, and we call this the exponential model. A silicon diode conducts a negligible current until the forward bias is at least at 0.5 volts. This is what we call the boundary for the fully conducting region. If you remember, we used that word in the beginning of the chapter. Then the current increases rapidly, with the voltage drop increasing by approximately 60 millivolts for every decade of current change. So that is a pretty drastic change. Small differences in the voltage applied across the diode will result in relatively large swings, or not swings, but increases in the current throughput. In the reverse direction, a silicon diode conducts a current on the order of 10 to the negative 9 amps, and this current is much greater than Is and increases with the magnitude of the reverse voltage. So if you look at the math, one would expect that the reverse current would be dictated by Is. However, the actual reverse bias current that we observe is greater than Is, and we talked about that before. That's due to some imperfections in the way that the diode is manufactured, and noise and heat and a whole bunch of other factors. So this is one place where the mathematical model diverts a little bit from the observation, the physical observation. Beyond a certain value of reverse bias voltage, and that threshold depends on the diode itself, breakdown will occur and current increases rapidly with a small corresponding increase in voltage. Right, we have our fully conducting region, and then eventually we have a breakdown which we said was non-destructive, meaning that you can pass that boundary and come back into the blocking region and the diode will begin to block again. Diodes designed to operate in the breakdown region are called Zener diodes. They are employed in the design of voltage regulators whose function is to provide a constant DC voltage that varies little with variations in power supply voltage and or load current. Again, if for more information on Zener diodes, I'll refer you to the textbook and perhaps we'll touch upon it in the recitation section a bit more. In many applications, a conducting diode is modeled as having a constant voltage drop, usually with a value of approximately 0.7 volts. This is what we call the constant voltage drop model. This was one of the 4 that we talked about. So there were 4. Just to do a quick review, we have the ideal model, we have the constant voltage drop model, we have the exponential model, and then we have the small signal model. This one is sort of in a category of its own because the application is unique. But going from 1 to 3, what we see is increasing complexity as well as increasing accuracy. So moving down to this bullet, a diode biased to operate at a DC current I, big D, has a small signal resistance shown here. So this bullet seems a little bit out of place, but it's pulling from our work in the small signal model. Rectifiers convert AC voltage to unipolar DC voltages. Half-wave rectifiers do this by passing the voltage through for only half of the cycle and blocking the other half of the cycle. We talked about 2 different types of rectifiers. There was the center tapped transformer full-wave rectifier, as well as this one, which is the bridge rectifier. Right, the difference, so for the center tapped versus the bridge, right, the center tapped required the transformer, which is one huge requirement. Here, there's no transformer required. Over here, we required only 2 diodes. Over here, we require 4 diodes. And there were some other differences as well. So for the center tapped transformer, configuration or structure, what we saw was that the PIV was higher. The peak inverse voltage experienced by the diodes was higher, whereas for the bridge rectifier it was lower. And so there were some other differences that I'll refer you back to that part of the lecture to discuss or to review. The variation of the output waveform of the rectifier can be reduced by placing a capacitor across the output terminal. And so this refers to exactly what we talked about last time, which was the use of a single capacitor filter in order to take out or reduce the ripple in the rectified voltage. And we saw there was really 2 ways of addressing this problem. If VR is large, then we have to use Laplace. If VR is small, then there were some equations that I forgot the 428, 429 that we saw we could use to estimate different aspects, amplitude of the ripple, conduction interval, etc. Combinations of diodes, resistors, and a possible reference voltage can be used to design limiters. We talked about that today. Applying a time-varying waveform to a circuit consisting of a capacitor in series with a diode provides a clamping function. We also talked about that today. And then also the voltage doubler, which is another topic that we talked about today.